But anyways, I can talk about that a little bit more in here. We're sitting at 12:10, so let's go ahead and get started with everything. So as we've got this stuff going on, this is our last lecture that is also going to show up on Exam 2. Exam 2 being this coming Monday, 5 days away from now. Same deal as last time. Remember, it's going to be open for a 24-hour window from noon of Monday, so right around this time on Monday until noon on Tuesday. So hopefully you've got some good time within all of that you can sit down for a couple hours and take that exam. Covering chapters 7 through 10, but it might have a little bit of sprinkle of stuff from 6 in it as well, because if you remember, chapter 6 is all about, where we introduced forces in the first place. And since everything 7 through 10 is forces and energy anyways, it fits in pretty well, right? Some of the questions you could argue fit within, multiple chapters or anything else like that. But before that, next class, if I just said that today is the last day of material that's going to be on exam 2, I generally don't like to cover more material before we take that exam if I don't have to. So instead, on Friday, we're going to have just a review day. I will be here for the full 4 hours, answering questions, working through problems, going through conceptual things, looking at old slides, all that good stuff. Anything that I can do to help you guys out, bring questions, right? That's the entire point of this thing. I can sit there and I can ramble on about things, but I have a better sense that you guys get more out of it if you bring some questions for me. So please do that. You're welcome to stay for the full 4 hours or anything else like that. If you feel like you've got tons of questions or you just want to see what I'm answering, or you can skip it, or you can stop by for just a little while, ask your questions, and then be out, whatever you want to do with that. I am happy for anything. Will that be recorded? I keep it on Twitch, but I don't upload it to Canvas just because by the time I've got that file size, it takes forever to upload, and it just eats up tons of space, and it's not something that is good to go back to in the same way. Kind of like how my office hours get recorded on Twitch, but I don't actually upload those in the same way because it's just not as, it's not cohesive material in the same way. Yeah, about entropy. But entropy and heat is not something that we're going to cover in crazy high detail anytime soon, right? We've got a little while before we get into that. But talking about heat and where that comes from in our context today is pretty important, right? Because so far we have had this random hodgepodge from chapters 9 and 10, seemingly jumping back and forth between a lot of these things. I'm labeling this as 10-2, but it's actually got a lot of stuff from chapter 9. Kind of on a similar note from that, because of how much we're jumping around and because yesterday was supposed to be a break, there is no reading for today either. We'll pick back up on that full steam ahead after exam 2. But for right now, we'll just relax with it a little bit. But within all of this stuff, we've kind of had a weird way of talking about these things. The order's been a little bit strange, but our big... The whole big shtick, right? The thing that we've been talking about the entire time is essentially there is a transformation of energy. We've talked about forces and kinematics and how that can be used to describe motion, but now we've essentially been creating another tool. That other tool is energy and energy conservation and where energy can go. And everything that we've been doing so far is talking about the different forms that energy can be in, but the big part of this is that in any system, the energy of that system should be conserved. And this will be exam material, yes. So the idea between conservation of energy here is that any energy that we might have in our initial state should be the exact same amount of energy we have in the final state. Now, it doesn't have to stay in the same form, and that's a big sticking point. Right? We might have kinetic, we might have different potential energies, we might have work being done. Any of those things might be factors in here, right? So when I'm saying Ki and Ui, this is any kinetic energies we've got, any potential energies we've got, as many as we might have, whether that's electric, gravitational, spring. There are other potential energies, but I'm drawing a blank of what they are right now. Any potential energies we have are all kind of wrapped up in that term right there. And they might be zero. Right? It might be that it starts with zero potential energy and just kinetic energy, and it ends with maybe some mixture of the two. Either way, any of these values can be zero, the main point of it is that the total energy on one side has to equal the total energy on the other side. So all of that time, though, we have been putting this big stipulation in here. That stipulation is that energy should be conserved. And our justification for that was anytime we have conservative forces, right? If parts of it are conservative and everything else, if the whole thing is conservative, then the whole thing's conservative all the way down. Conservative forces, conservative energies, all of that good stuff. That is to say, the total mechanical energy of a system should be the same the entire time, right? It's a constant value. At any step, step 1, step 2, step 3, step 4, step 5, any of the steps in the process, it should have the same energy the entire time. So we can either write that out as one big energy equation like this, or we can write it out as a change of energy equation, whichever one you like a little bit more. Mechanical energy is energy associated with movement, specifically here. Right? That's what that means, as compared to thermal energy. Mechanical energy is all about our potential energies and our kinetic energies. All of the movement things. So, and there's a few different ways that we can write these things out. These things are really long, but this is like what we could do for the change of kinetic energy. This could be the change of gravitational. This could be the change of spring energy. All of those things can be really long equations. It just depends on what's actually going to be there, right? Most of the time, we don't need every single one of these terms for a problem, right? And a lot of our problems so far, we haven't even seen springs. So why worry about that? If there's no change of height, then we don't need to worry about gravitational. If there's no change of momentum or anything else like that, then there's no need for kinetic energy. We just have to pick and choose what do we see in the problem, right? That's the big thing. But this entire time, I keep bringing this up, conservative forces the entire time, and I've mentioned what happens when we get away from that, but this picture right here is essentially some sort of modeling of two rough surfaces moving against each other, right? If you really zoom in, friction is essentially all of these rough surfaces pushing up against each other. And as they push up against each other, all of these, I want to call them micro collisions, right? Of all of these different ledges and valleys and everything else like that, the energy that we had goes into different places. And we can imagine this. We know it's a non-conservative force because friction, for example, we know it depends on the path. I know that friction is going as, let's just go ahead and write this down. I know that friction goes as that friction coefficient times the normal force. So then the work done by friction, remember friction always opposes motion, right? It doesn't pick and choose what motion it opposes, it always opposes motion. And so that means anytime I'm looking at work done by friction, that's just my friction force times essentially however far I travel, times distance. So if I take path 1, versus path 2, shown in the picture here, friction is going to be doing more work along path 1. It's going to be taking more energy along path 1 because it has a longer distance that it's allowed to travel, right? And why is that? Why is that so different from gravity? What's the big difference between friction and gravity that makes friction a non-conservative force here? What's it about the force specifically? Gravity doesn't care about the path taken, but why? What's the stipulation? Why doesn't gravity care about the path taken? It's not even that gravity's always happening. I could argue friction's always happening. But the key is that gravity was always pointing straight down. Regardless of what path I took, the force from gravity was a constant, whereas friction will change depending on the path I take. If friction was always pointing the same direction, regardless of what path I took, then maybe we could be a conservative force. But the fact that friction changes its force depending on the path, that immediately strikes it down. We say there's no way it can be a conservative force. It changes. It depends on the path. Now, we also know that it, always opposes the motion on top of that, so we run into an issue on that side. But that's why we can't store energy in friction in the same way, right? And what happens to that energy? Well, it goes into other places. It goes into typically, mostly thermal energy. But thermal energy what we will find eventually, you've got to take me at face value for this right now, thermal energy is really hard to convert into mechanical energy. Does anybody know, roughly speaking, like what's the efficiency of burning coal to electricity? Does anybody have a good idea on the efficiency that we can do that, or nuclear power, or anything else like that? And I'm not talking small scale stuff, I'm talking about the state-of-the-art power plants. 60% is way too high. 20 or 30%. Yeah. 20 or 30% is what we're getting. Maximum efficiency, state-of-the-art power plants. The fact of the matter is that there are limits on the efficiency of heat to mechanical conversion. We can't simply make that conversion over in the same way. It doesn't work. It takes a lot of effort to actually make that happen. We have to be very careful, but there are limits, there are laws of thermodynamics that stop us from getting any more efficient. And that's a big deal, right? And that's why we consider this kind of a non-conservative force, because mechanical energy to heat energy, it's kind of like a one-way door, right? We can clearly, when we push things around and everything else, there is heat generated, right? Go back to our like rubbing our hands up against each other kind of style here, right? When we do something like this, any energy that we had, so we put all of that work in, right? You can feel it. Your arms put some effort in, right? Think about the mitochondria providing all of that energy for the cells in your arm to go back and forth like this. Surely there was some energy exerted by those cells. But now my hands have no net kinetic energy at the end of the day. There was other things stopping it. Right? There was work done in a lot of different directions, but I have exerted some energy, and everything that I'm left with is essentially just heat. I can't just convert that heat back into mechanical energy. State of the art is getting like 30% conversion, but even for smaller things like this, right? A power plant designed for extracting mechanical energy from thermal energy can only get around 30%. Our arms, the book sliding across the table, we're not getting anywhere near that. So that's why we call this dissipated energy, energy lost. It's not that it's lost, it's just that converting it back from heat into mechanical energy is nearly impossible. Or it is a trivial effort. Not a trivial effort, what am I thinking of? What's the word that I'm missing here? It's, there's a good word for just simply not worth the time. Whatever it is, it takes more effort than it's worth to try and extract that back into mechanical energy. So there's a couple different ways that you can do this, right? And I've got my style, but the general way that I know the book likes to talk about this is that anytime I were to have some sort of non-conservative force, a non-conservative work done, I could always say that the change in mechanical energy is equal to the change from that force, right? The work done by that force. This is one way to write this out. I think instead, I typically prefer to include it somewhere. So, for example, when I'm talking about some of these things, if I were to watch a book sliding across the table. So initially it's sliding, it's got some kinetic energy to start. At the end of it, it has lost all of its kinetic energy. All of that has gone into work done by friction. That's how I like to write these out. I still like to do my initial versus final. I just like to essentially say, hey, some of that energy went into friction, right? That's another place that energy could go, from kinetic or potential or work done by friction or things like that. I like to include it as another term. That's an alternative way to do this. Whichever method makes more sense to you, that's the one I'm going to recommend you use, right? You don't have to follow mine. If you like the delta E, fantastic. Keep using delta E. I don't like delta E quite as much. It doesn't make as much sense to me. But if it works for you, that's fantastic. Keep on keeping on. So, I want to try this out though, right? We know what friction is. We know the equation for work. Remembering that work is equal to the dot of a force with a distance. So let's imagine this. A horizontal spring with spring constant 100 newtons per meter is compressed by 20 centimeters and used to launch a 2.5 kilogram box across a frictionless horizontal surface. So no friction to start. After the box travels some distance, the surface becomes rough. The coefficient of kinetic friction between the box and the surface is 0.15. How far does the box slide across the rough surface before it comes to rest? So think about where the energy starts. Think about where the energy ends. Use those two in the next 3 or 4 minutes here and see if we can come up with an answer, and then we'll look at it together. All right, so let's start taking a look here. So let's start by drawing out our picture. Who knows what it is? So let's just redraw that same stuff from before, squiggly section, all that good stuff. We've got a block, we've got a spring, it's been compressed by some distance. So I'm just going to kind of include everything all at once here. So I've got that. I'm going to say this is my initial delta x, whatever I have converted the spring, or compressed the spring by. And then I'm also going to draw out, we have covered some distance when the block has stopped. So here's state 0. Before we have actually released it, we have everything compressed, or our initial state is probably what I should better say here. Let's go ahead and say initial and final. Do I have to care about the kinetic energy of the block at any point? What do we think? No. I could. There's another way that I could do this problem. So let me kind of talk through what I'm going to do here. I'm going to use an energy conservation between my initial state and my final state. And I'm going to use that to find whatever information I actually need here. But realistically, I could find the speed before we hit the rough surface. Because if I had presented this problem to you as a block is moving with some initial speed, and it slides across the rough surface until it comes to a rest, you could just say, hey, I recognize that's kinematics. It's got an acceleration from the friction. That slows it down. It's going to move some distance before it ends up at speed 0. And we could solve that with kinematics just fine. And, you know, I'm not necessarily here to stop you, but I am here to show you that energy could be a much faster way to do that instead. So let's call this distance, wherever we start from the beginning of the rough surface to where we end up now, let's just call that one, well, let's call it delta S, some path that we take over the rough surface. So then, what I've got between these two, I would say, all right, well, whatever I've got at the beginning here, the energy that I've got compressed in the spring right now is 1/2 k delta x squared. Where all of my energy went to the very end here should be in this friction, right? Friction took away all this energy, right? We can see somewhere in the middle here, I would have had a bunch of kinetic energy, and then we would have started sliding across the rough surface. We would have lost all that energy to the work done by friction. So how much work is done by friction? How do I actually write that expression out? Well, I can just say work is equal to the force dotted with the displacement. In our case, well, let's draw the free body diagram. Let's kind of prove this. What's going on when we're over here? I know I would expect a normal force. I would expect a gravitational force. I would expect a friction force. Does that cover it? Do we agree on that one? I think those three, and that's about it. While I'm here, I might as well also say, hey, we had some initial motion that was going like this. This is where we were going. That's why friction wants to point to the left. You know, at the very end, we're stopped, but while we were still moving, that's the way that we were moving. So then, can we all agree the normal force should be equal to just mg? Right? Because I'm looking at this block, it's not flying up, it's not flying down. Those two forces should balance out. Then friction, because it is kinetic friction, should be mu k times the normal force, should be mu k times mg. If that's the force from friction, then the work done by friction, can we all agree that delta S and F of k, they're pointing, well, opposite directions here, but they're pointing essentially along the same axis, right? So that dot product, we don't need to worry about that dot product. So I would say, all right, well then my work done over here would just be my friction force times that displacement, delta S. Now, why haven't I written, what have I perhaps forgotten here? What am I leaving out of this expression right here? Does anybody know? I've got everything so far as far as it goes with the forces, with the displacement. I've got an expression for f of k, and I'm not worried about that, but what isn't here that maybe should be? What have I neglected from the dot product itself? Would it be negative? That's a really good question, and that is exactly what I'm leading on to here. Here's the way that I think about this. Why I'm not including a negative sign. If I were to do this in the delta E style, if I were to say my change of mechanical energy, as I might have it, would be equal to the work done by friction. That would be, the change would be a negative f of k delta S. There, I would absolutely agree, because we had some energy and we were left with nothing. At the very end, we have no energy left. No kinetic energy, no potential energy. But at the beginning, we had a bunch of spring energy. So arguably, yes, the change would have been negative. We went from a positive value to 0. Here, though, when I do it like this, I have this in a little bit of a different way. And these two styles do agree, but what I'm basically saying is that this is where energy was to start. This is where energy is at the end. Both sides are going to be positive here. The other way that I can imagine this is that I'm taking away from whatever I had at the beginning. So if we were to even write this thing out, if we were to say this change of energy is equal to our final energy minus the initial energy, that's what's equal to negative, whoops, here's my delta S. Then what I could be writing here, this can become energy final plus whatever's done by friction is equal to the initial energy. That's just a little bit of algebra rearranging this thing. But I like this description a little bit better for myself. Again, if you like this delta E style and that works for you, fantastic. I'm not here to change that one. The reason I like this one, though, is because this is saying this is the final mechanical energy that we've got, but this is some other place that energy went. All of this together is where the energy's at in the final state. Right? Some energy went into friction. Friction hadn't had any energy to begin with. There was no energy allocated for friction at the beginning of this problem, but by the end of it, friction has stolen some energy for itself. But it's kind of an extension for myself here when I'm talking about the final versus initial energy. So that's why I'm leaving this one as a positive in this expression right here. I think it makes more sense, in my mind at least, to say, well, this is where the energy was at the beginning, now this is where the energy is at the end. And if we do this, if we take this as we've got it here, then I'm going to take these two expressions and I'm going to set them equal to each other. Let me erase that circle, makes it a little bit more confusing. So let's put like a big equal sign between these two. These two should be equal. The things that I know, I've gone a long enough time without actually stating my variables. I know that I have 100 newtons per meter for my spring constant. I know the initial compression was 0.2 meters. I know the friction coefficient is supposed to be something like 0.15. And I also know that the mass should be 2.5 kilograms. We are looking for delta S. We want to know how far across the surface we have gone. So I can take this expression. I can say that delta S should be equal to, here's my spring energy, divided by the friction force. And there's not really a ton of simplification I can do on this one, right? It's kind of just already in all the variables that we might want to have in here. Plug in everything in. What do we find at the end of the day? Well, 544 meters. So how do we feel about this? Does that description make sense about where the energy is going, how we might be splitting up the energy? The two methods, you're either going to take this from delta E, or you're going to take this from a term of final versus initial. So if we were to say this was going to be delta E, then I would say my change of energy, whatever energy I would have, it would be the final energy minus the initial energy. In this case, what it's really saying is that we have 0 at the end. We start with a bunch of spring energy. But whatever change of energy I have is equal to the work done by non-conservative forces, specifically here friction. The work done by friction we saw was negative. The force points in the opposite direction of the motion, so it's a negative work being done. That's one way to go through this problem, and it comes out with the exact same algebra at the end of the day. The other way is to say, hey, friction is just another place where energy can go. At the very end, some energy has gone into work done by friction. Where I started was energy in the spring. I can simply have another term. This term right here says, hey, this is all of the work done by friction. This is where that energy went in my final state. Either way, the algebra works out to be the exact same in either case, but it's kind of how you conceptualize what you're doing with the energy. And I do appreciate the motivation every single time somebody says, could be worse. We love that motivation, right? Because that's exactly what we're going to use for our next problem here. Let's go ahead and take a look at it. So let's imagine Kathy's baby brother sits on a sled. The combined mass of the sled and the baby is m. Kathy pulls on the rope at an angle theta above the horizontal. The tension T is constant. The coefficient of friction between the sled and the snow is mu sub k. Find an expression for the speed of the sled after it has been pulled some distance d, if the sled started from rest. So, think about this a little bit. It's going to be a little bit more complicated. Our friction term is going to look a little bit different than it did from last time. Because tension, as we can kind of see in this picture here, tension is pulling both in the x and the y direction. So I would recommend start with a free body diagram. It's a necessary step. It's very helpful. Once you've got that, think about what goes on here. What actually provides, we didn't start with any kinetic energy. Right? We're not changing height. There's no springs. There was no kinetic energy to start with. So why do we move? Why do we have kinetic energy at the end? Where does that come from? And I want you to take that idea, think about where that's going to be coming from, run with it. We're going to come back in the next 5 or 6 minutes and see what you've got with this one. So our initial energy is 0. For anybody looking at that one, we do end with some kinetic energy, but our initial energy should start at 0. It is work done that gives us our energy. But take the next 5 minutes or so, jump on that one, see what we get. All right, so let's start taking a look. And I'm going to kind of blitz through 3 different ways that you might view this problem here. Regardless of which way you decide to go with this thing, the fact of the matter is that we absolutely need to have some sort of good picture drawn here. So, this is a good depiction of a sled with a baby in it, I think. I'm going to start with my free body diagram, because I think that is probably the single most important thing to have here. We know it is in contact with the surface beneath it. There is going to be a normal force. We know gravity pulls on it. There is going to be a gravitational force. We know there is a tension pulling on it upwards, just like this, at an angle. Let's go ahead and do this in like a dark gray here, dotted line, theta. And we also know that there is going to be, if the motion is going this way, in green please, so it stands out a little bit more. If the motion is supposed to be going this way, we'll just label that motion, then friction opposes that motion and points like this. So, a lot of different things that go into this one. I'm going to draw some axes because with enough forces like this, we should probably do things all good and proper here. Think about what we are given. We are given what that tension is. We are given the mass. We are given the friction coefficient mu. What else do we have? We've got the tension, we've got the mass, we've got the friction coefficient, we have the distance traveled. And those are m, theta, t, and mu. Oh, we also have theta. That is an important deal. Theta, not just shown in our picture. All right, and we are asked to find the final speed. So, again, this could completely be done with kinematics alone. Right, and we can also, I guess, say that our initial speed was 0. We could do this entirely with kinematics, though. We could say, hey, there is going to be there's not going to be a y acceleration, but there is going to be an x acceleration. Then whatever distance we travel, the acceleration, we've got the initial velocity, we can find the final velocity right from that. That would work. And if you're in a pickle, if you're on the exam or something else like that, and you're like, oh, I know I can use energy, but I'm not sure how, you can always go back to kinematics. Right? Nothing wrong with that. It might take a little bit longer, but it will certainly get you there. But I want to talk about this in a few different ways of how we might approach this from kinematics. So, for example, let me go ahead and do this thing in terms of, let's think about the best way to start with this one. Let me go ahead and write this out in terms of change of energy to start. So let me take the delta E method. Change of energy, which is specifically the final energy minus the initial energy. We know at the end of the day, where's all of our final energy going to be? What form is it going to be in? What do we think? Yeah, kinetic energy, right? We're moving to the end. There's no change in height. There's no change of a compressed spring or anything else like that. So if we're talking about what mechanical energy do we have at the end of the day, I would say it's all kinetic energy, and then our initial energy would have been 0. One half mv final squared. That comes from whatever non-conservative forces are acting on this sled. Specifically here, the two that I'm thinking of, there is going to be some work done by tension. So let's write that out as work done by tension. And I see tension points in the direction of my motion, so that's going to be a positive quantity. I see my work done by friction. Let's go ahead and just write this out as negative. We know we're going to plug in mu. Well, let's just go ahead and add a plus for now. Let's say plus. These are the two forces that are going to be doing work while the sled is moving. Let's talk about what each of these are. Let's start with tension. We know anytime we're talking about work, work is always equal to that force dotted with our displacement. So what's that expression look like? If we're thinking about the work done by tension, what does that expression look like for work done by tension? What do we think? Work done by tension should be equal to what? Let me write that a little bit bigger. But what are we thinking here? What should that expression look like? T dotted with D, I would agree with that, but probably the better way to write this out, I'm not going to do this in component form. Instead, what I could say is TD cosine of theta. That's the angle between the two of them. TD cosine of theta. Perfect. That's it. That's done. That is the work done by tension. Because again, part of tension is pulling up. That part of tension that's pulling up isn't doing anything for our motion, right? That's just pulling up on the sled. Now, the work done by friction is going to be a little bit more difficult here. So let's go ahead and write that out to start here. I would say the work done by friction is going to be, well, dotted together, the motion versus friction, they're on the same axis, but they're pointing in opposite directions. So perhaps the easiest way to write this one is negative force of friction times D. My force of friction is a little bit more complicated though. So let me go over to dynamics land for a little bit and let me say, all right, well, what forces might be going into that? I know that my force of friction would be equal to mu times the normal force. What is the normal force equal to in this case, though? Yikes. I need to look at the y direction. I need to say that there is no net force in the y direction because, again, I assume we're not just sending the kid flying or anything else like that. No work done in the y direction, or no force, no net force in the y direction, means that the normal force plus the sine component of tension minus mg is equal to 0. That is to say, the normal force then should be equal to mg minus t sine of theta. So our expression for the work done by friction ends up being negative mu k, and I'll just put my d right here, times mg minus t sine of theta. So this one is certainly a little bit more complicated. There's some more moving pieces to this one here, right? But that's okay, because now we're finished. And we really are. Let's go ahead and plug into our expression. Now we have the two works that we need. We've got the work done by tension. We've got the work done by friction. They're all in terms of given variables. We can come back to this thing. We can say, well, this now looks like 1/2 mv final squared is equal t d cosine of theta minus mu k d this mess, mg minus t sine of theta. And I know the expression isn't particularly kind, but it works. Then we're just solving out for phi of f. Multiply everything by 2, divide by m, take a square root. Which is not very kind. So let's try and do it. Here's a final expression as we can write this thing out. Those are the couple steps that we've got left. I'm going to say maybe the easiest way to do this is 2d over m. I'm just going to pull that to the outside here. Bracket t cosine of theta minus mu mg minus t sine of theta. There's unfortunately just not a nicer way to write all this stuff. Square root of that entire thing. So that's maybe not a super kind expression. But the process to get there is not anything crazy. And in doing this, we can almost kind of end up seeing where a lot of these details came from in the first place. Right, our v final squared is equal to v initial squared, which was 0, so it doesn't show up here, plus 2 times the acceleration times the distance. This nasty thing right here is mostly our acceleration in the x direction, divided by m, or that rather, it would have been the force divided by the mass gives us the acceleration in the x direction times that distance times 2. And the work done by friction is negative because the force of friction is in the opposite direction as motion. Yes. So this is one way to consider this problem. Now, here's an alternative idea. What if instead of this, I said, so this is one way to solve this problem, and that's a solid way all the way through. What if instead I would have said my change of energy is equal to energy final minus energy initial is equal to the total net work done by non-conservative forces. Then what I would have done is I would have said my net work is equal to my net force dotted with D. That is to say, this would have become my T cosine of theta, going in the x direction, minus, oh, we're going to have some nesting brackets here, mu times mg minus T sine of theta, times D. This would have been my alternative way to do this. This would have been my net force in the x direction with D. And we can kind of see it's the same thing, right? Essentially, we get back to this exact same step, even if we look at it like this. But it's a little bit of a different way to conceptualize it, right? We're either looking at the individual works being done, or we're looking specifically at all of the forces summed up together first. So let me solve out all my dynamics first and then take that into energy, rather than taking it piece by piece. The third way that I can consider this, something slightly different and a little bit more in line with what I like to do with this, I would say my final energy versus my initial energy. So for my initial energy, this actually includes work that I'm about to put in. So for my initial energy, I would have said, I am about to put in all of this work done by tension. And that should equal my final kinetic energy, and then whatever energy went into friction. And this is where it gets a little bit spicy because my sign for this is a little bit backwards. Right, again, it's a slightly different way to conceptualize it, but this is the third way that I can imagine this. Now we have to be careful in this case because that one is a positive mu times the normal force times D instead of a negative because energy goes into that one. When I take it like this is always, everything is always positive. I just have to put it on the right side. But these are three separate ways that you can try to conceptualize what's happening to the energy. However you would like to conceptualize this. We can find one method that works well with our understanding of what goes on with the energy. So how do we feel about this? Does one of these three methods mesh? You know, does everyone have at least one method that they're like, yeah, I get that? All right. So let's keep taking a look here. I've got one more for us. Let's imagine a block of mass m starts from rest at height h. It slides down a frictionless slope, then across a rough horizontal surface of length L, then up another frictionless slope. The coefficient of friction on the rough surface is mu sub k. Find an expression for the height of the block as it slides up the second slope. So this one's a little bit tricky because there's this kind of intermittent thing, right? When we're thinking about that final energy, friction has messed with us somewhere in the middle. So you've got to consider that. But I want you to take perhaps the next 4 minutes and work on this one, and then let's see what you've got. All right, let's start giving this one a go. So, aside from all of this mess, first things first, we need a very good picture to help us here. I've got a slope. I've got a flat surface. Let's try to make that actually look kind of flat. I've got another slope. On the bottom here, on this flat surface, it's kind of rough. Let's assume we can even round out the corners or something else so this thing slides nice and even. But we start with a box up here. Something like this. Some height h above the ground. So like right around there. Let's call this h initial. At the very end of this thing, we're going to slide across friction, and conceptually, what would happen here, friction's going to slow it down. Right? It's like the bouncy ball never comes up to the same height that you dropped it at. It always comes up just a little bit lower because there were vibrations, there were other places that energy was lost. So then, let me draw this one a little bit lower to say, hey, we don't end at that same height. We end a little bit lower than what we started with. Something like that. Call it HF. And then between, there is this friction coefficient mu and a total distance. What did we call this one? Length L. So let's do this in like a light gray. L going from here all the way up to here. Okay. So again, a few different ways to think about it. Let me start with that delta E way. Say, all right, well, my change of energy, as I would have it, this is equal to my final energy minus my initial energy is equal to whatever work is done by non-conservative forces. That is to say, my final energy should be mgh final minus mgh initial is equal to this work that's being done by friction, right? It should be a negative quantity because we're losing energy to friction. We're not hitting the same height as we did before. So this is going to be negative force of friction times that distance L. What is my friction force in this problem? Do we have anything crazy? There's not a whole lot of forces acting on this thing, right? We can draw this thing out just in case. But while we are on the slope, or the flat ground with friction, I've got a pretty simple picture. I would have a normal force. I would have a gravitational force. I would have friction. That's all I expect to see. That means my normal force should be exactly balanced out with gravity. So my friction force should just end up being negative mu times mg times L. I don't need all those m's, and I'm looking for hf. So I'm going to divide everything by m. I'm going to divide everything by g. I'm going to move h naught to the other side. hf is equal to h naught minus mu L. Do we have any kinetic energy in either our initial or our final state? Looking at my picture here. No. In the in-between, I could consider kinetic energy if I was interested in the in-between. If I wanted to know the max speed, for example, then I might need to consider the in-between spots for that kinetic energy. But my very first state is all gravitational potential. My very final state is all gravitational potential. And friction, there is some work done in the middle, but kinetic energy we don't really need to factor in here at all. Now, again, the other way that I could consider doing this problem is to say the energy that I start with should be the same as the energy that I end with. mgh naught is equal to mgh final, and at the very end, there is some heat that was dissipated, right? Some friction force done. Friction would have eaten up some of that energy. So this is the alternative way that I could have written this out. This is my initial energy versus where all of my energy ended up by the end. And this is the exact same expression that we just found. There's no difference here. It's just notice that h naught and hf are on opposite sides. So again, I can divide by mg, get rid of that, get rid of that. That is h naught is equal to hf plus mu times L. That is h of f is equal to h naught minus mu times L. Same expression as before. However you would like to consider these. Whatever works conceptually, that's the equation I would use. I mean, the other way that they do, when they're talking about the energy charts at the very, very end, they're basically saying this method over here. Because what this is, talking about friction, that's our change of E thermal, right? Because we keep talking about this is where it goes. It goes into heat, it goes into vibrations, other stuff like that. That's all thermal energy. So that's what that term is right there. That's how friction steals away that energy, takes some of the energy out of the mechanical system. So yeah, and it is kind of nice. The book talks about it in both ways, but I think by the end of it, when they're talking about the energy charts and everything, I think it's very useful. I think it's just, again, you don't have to necessarily have mastered both methods necessarily. You just have to have one really solid. You've either got to be thinking about what goes on with the change of energy, or you've got to be thinking about what goes into the initial and the final states. They're both saying the same thing, but in a slightly different way. All right. So, talking about some of these things. We have so far, and I can move myself, where can I move myself? What about over here? Yeah, let's go over here. So now you can see all that stuff. So far, we have been talking about getting work from force, right? And specifically when it's a conservative force, we get a potential energy associated with that. And that's usually how we have been treating this, and that's the only way that we've really been thinking about it. We have some forces acting, then we end up getting some energy out of that, and that's all fine and dandy. But we can take that in the opposite direction just as well, right? If we know what a potential looks like, we can find a force from that. Now, keep in mind here that what we're going to be finding here is not necessarily the force from any single one potential energy. Right? If there is some sort of potential energy or anything else like that, then what we are finding is the net force along that direction because of the grouped together potential energy. So if there are multiple potential energies all acting at once, if there is spring, if there's gravity, if there's electric, if there's magnetic, if there's a lot of different things that are creating some sort of potential energy, all of those things sum together, F of x is what we would find the net force in the x direction because of all of those together. So it's not quite the same thing as looking at the individual forces anymore. We're getting like grouping all of that information together, kind of glossing over the fact that it's individual forces. But this is a way that we can go from energy back into forces, just taking a derivative now instead of an integral. So, and that is just a derivative of x. And because we have been talking about this, because the potential energy, or rather the change of potential energy, is the negative of the work done by a force, so too, when we take the derivative, we need to include that negative sign just in the same way. Right? Don't forget that one. So finding the magnitude of this is one thing, but it's kind of like the idea of, you know, think about being on top of a hill, a ball on top of a hill versus at the bottom of the hill. At the top of the hill, it's got the most potential energy. It speeds up, the force pulls on it, goes downwards as it rolls down the hill. It opposes, you know, goes with the opposite of the change of potential energy. So, let's try this real fast. Let's imagine that we have this graph of the potential energy, and I'm not going to say what this is from. Maybe it's gravity, maybe it's electric, maybe it's who knows. But a particle has potential energy as given by this graph. What is the x component of the force at these three places? 5 centimeters, 15 centimeters, 30 centimeters. I'm going to give you guys just a couple minutes to work on this one, and then we're going to check what numbers you got. All right, what are we thinking here? Do we have any answers to any of these things? Jump into it like this. Do we have any good answers on forces or anything else like that? Any guesses or anything? When I've got a graph that's got a lot of linear pieces, and I need to take a derivative of that, most of the time, I have a much easier time than actually creating some sort of function or anything else like that. What are we looking for? Slopes. Exactly. That's all we need. So at 5 centimeters, I can say, hey, this is a full linear portion all right through here. So if I find the slope of that section of line, I will have my force along that section of the graph. That is to say, we change. So force is going to be, these are large scale things, right? So I can just say negative delta of the energy divided by delta x. That is, for part A, what we would see. My change is negative 10 over, not 10.1, right? Newtons use meters. The graph is given in centimeters. So my change of distance is actually 0.1. The negative cancels out. I'm left with 100 newtons of force along that path. B, what's our force? We've got this one. Come on, what are we thinking? 0, there we are. 0 newtons of force, nothing. Part C, same deal again. I'm going back up to 10 over a rise of 20. So that is to say, a negative, the change is a positive 10 in our potential. We do that over 0.2 this time. So over this span, it's negative 50 newtons of force. And those are our 3 answers. Oh, I'm covering that up again, aren't I? Shoot. You can see that one. Sometimes it just, I end up covering up my own writing when I end up working out solutions if I stay on the left side here. But how are we feeling? Does this all make sense? Are we vibing with it? Or are there any questions that I can help clarify some of these details right now? Go. All right. Nothing too crazy in this one. The 0.1 and the 0.2, that is our delta x. So when we're talking about finding this slope, my 0.1 is my 0 to 10 centimeters, but I want to keep that in meters because meters are my standard unit. If I were to plug in 10 instead of 0.1, then I find, what would that be? I know there's a special name for these things, but I don't know what they're called. It wouldn't be newtons, is what I'm trying to get at here. If we want to get newtons of force, then we need to make sure we're in standard units. We need to make sure we're in meters. It's got to have some stupid name, I think. But whatever it is, I only know the smaller ones better. All right. So let's try this with a little bit less slope, a little bit more derivative. A particle moving along the x-axis has the potential energy 10 over x, and that's in joules, standard units. What is the x component of the force on the particle at 5 meters? Take the next 2 or so minutes, see if we can come up with a good answer here. All right, and same deal as before. Let's take a fast look at this thing. So probably the best way to take this derivative is, I don't want to deal with this thing over x or anything else. There is technically a division form of derivatives, but it's this nasty equation, and why would I bother with that thing when instead what I could say is that my potential energy is equal to 10 times x to the minus 1 power. 10 is a constant, it just sticks around. Then I take the derivative on x. That is to say, du dx would look like this. 10 sticks around, the negative 1 comes down, and we subtract 1 from that. So it turns into x to the minus 2. That is, our full derivative would be something like negative 10 over x squared. Now that's only the derivative. Remember that the force is equal to the negative of that derivative. So that negative that we see in our expression here is going to become a positive 10 over x squared. That's our force. At any point, we plug in 5. Force at x is equal to 5. That is 10 over 25. What we should find is that the force is 0.4 newtons. How are we feeling about this one? Connecting the two sides of this thing, whether we have to do this graphically or analytically, we've got all of those tools. No worries there, right? If we're still feeling unstoppable about all these, if we had the graph, the result is the same. Yeah, sure. It's just the issue that we run into with this one is that the graph is, you know, non-linear. My graph, as I would expect to see it, is something like this, which finding that slope's a lot less easy. We could approximate it, of course. But it's with the non-linear stuff, it's much better to just do the analytical form. Get a lot more accurate for, you know, a lot less effort. So remember here, when we're talking about the force as it pertains to this expression, there is a negative sign right here. Right? Because when we had first defined potential, or specifically potential energy, when we'd first defined potential energy, we said it was the negative of the work. So there's a negative sign out in front of our integral. So to make that transformation back, we need another negative sign. The negative sign can't just come out of nowhere here, or it can't just disappear into nothing. So there's a negative sign in front of this derivative. So when I'm taking this derivative here, that is not considering the negative sign. Then when we say force is equal to the negative of that derivative, that's why the negative sign cancels out. Kind of actually in the same line, whereas we saw the negative slope has a positive force, the positive slope had a negative force, that kind of same deal. That's the behavior that these things see. All right, so we don't have a whole lot left, but I do want to talk about one more thing. Maybe this is a term you're pretty familiar with, but there's a few different ways to talk about this one. Thinking about power. We've got a specific definition for power. That definition for power is the rate of energy. So you might be used to hearing things in watts, right? If you think about like regular old incandescent light bulbs, because I keep talking about incandescent light bulbs, they're like 50 watts, 100 watts, 80 watts, 150 watts for the really bright ones, stuff like that, right? All of those values are measured in watts. If you've thought about computers or anything else like that, you bought a power supply that maybe supplied 900 watts. It's a pretty beefy one. Your phone goes on the order of 10 or 20 watts. The 1.21 gigawatts. Yes, same deal as before in that one. Right? All of these things, they are units of power. And I don't want to get too far into this or anything else, but why would we measure like electronic devices in units of power rather than units of energy? They get the Energy Star rating, but they're measured in units of power. What's up with that? Why do we do that? Why does anyone think? How many hours is a light bulb going to be turned on? I don't know, right? I don't have my light turned on right now. It's the kind of deal of we give these things in units of power because who knows how long the thing's actually going to be turned on. And that's a really big difference, right? If you have a light turned on sparingly, it's not going to use much energy. If you have it turned on constantly, that's going to use a lot more energy. So instead, we talk about the rate that they would be using power, assuming that they're turned on. But what do we actually do with that? We measure these things in watts, and 1 watt is just equal to 1 joule per second. And this is kind of a fun thing if you really start to think about those differences, how much thermal energy things have versus mechanical energy. Think about taking like a 2 kilogram book and moving it up a meter. That's about 20 joules, give or take. A low brightness old incandescent bulb does 2.5 of those in a single second. The energy for a lot of electronics is wildly different from a lot of the things that we're used to dealing with for our regular mechanical kind of motion here. So it's a really fun transfer of, you know, what sort of different energies do we have in a lot of these different devices. If you're using a laptop, that's generally on the order of 90 watts. So that's, you know, a 1 kilogram book or something else like that lifted up 10 meters every second is what a laptop takes. Whereas a phone, on the other hand, is single watts. But anyways, generally speaking, at any time, we can always find the power as it relates to mechanical energy like this, or a system in general, as the rate of change of energy. Where does change of energy come from? Work. So power could also be written as the derivative of work being done on an object. Right? When I'm talking about lifting up a book or anything else like that, I'm thinking about the rate that I'm lifting that book up. Of course, eventually, if I have some initial height and some end height, there's going to be an amount of energy transferred. But the quicker I lift, the faster that energy is transferred, the more power I'm exerting on that book. That is to say, we can write that out as force times velocity, right? Instead of being dotted with a displacement, now it's dotted with velocity, because I assume that my force is constant. If my force is not constant, then we've got some more work to do. But this is, generally speaking, going to be true for any sort of constant force acting over some distance. So if you're thinking about cars or anything else and the horsepower that an engine provides, a horsepower is a unit of power. That's talking about how much force can it exert given a certain speed. Stuff like that. Let's try this, though. Let's say that we have a 10-kilogram block of steel and we are sliding it across the table at a steady speed of 1 meter per second. And we do this for 3 full seconds. The coefficient of kinetic friction between steel and steel is 0.6. Notice we are pushing it. We don't know how much we are pushing it by. How much work must you do? And what was your power output while pushing? I'm going to say take the next 4, maybe 5 minutes to work on this one, and then we're going to take a look together. Let's start taking a look here. So, one key detail that we absolutely need to take with us. Steady speed. Steady speed means what? There's a couple things that I can extrapolate from that information, but there's a few really big ones. What does it mean to be going at a steady speed? Acceleration is 0, I would agree. Could mean a couple different things, though. I could think about that in force. Right? Because if there's no acceleration, then the force that I'm pushing is the exact same, cancels out with the force from friction. Or I could indeed think about this as kinetic energy doesn't change. If we're at a steady speed and we're not moving up a slope, we're not moving down a slope, there's no springs involved, the change of energy of the full system is 0. That is to say, all of the work that I'm putting in is exactly the same that friction is taking back out. So since I need to find work anyways, I can just do that. But one of the ways that I could treat this is I could just say, hey, take whatever power that friction has and work with that. But anyways, let's write down some of these details. Let's draw ourselves a good picture here. Let's get all of the things that we know we're going to need for this thing. Not that, this. And we'll go up to perhaps here. Draw this thing out to start. We've got a flat, level ground, and we've got a big old block of steel, right as we do. Everyone, if you want to demonstrate with your own steel blocks at home, you're welcome to try this one. So we know that there is going to be a normal force. We know there is going to be a gravitational force. We know that there is going to be what I will call a force applied. That is the force that I'm putting into this thing. And then we also know that there is friction pulling back on it. Free body diagram, even if we're not going to dive into forces too much, it is just useful for the reference, if nothing else. So we've got all of this information about it, but we know that velocity is constant. We know that velocity for the entire thing, we need some of these details here, is 1 meter per second. We know that the mass of this block is something like 10 kilograms. We know that the time that we're looking at this is 3 seconds long. We know that the coefficient of friction is 0.6. We're looking for two things. find work that we put in. Call it work applied. We are also looking for the power applied. So we don't know anything about this force right here, but by the fact that we know the acceleration should be 0, we can either say that the force applied is exactly equal to friction, or we could say that in quantity alone, not necessarily looking at whether these values are going one way or the other, positive or negative or anything else like that, but in magnitude alone, the work applied should be exactly equal to the work done by friction. Something just like this. Right? Then, same deal as before, we could say that whatever power we put into this is so too the power of friction. So really, the only thing I need to worry about is what's friction doing? Right? I really don't care. Whatever this applied stuff is, I don't care to find that. It doesn't bother me whether I need to find that or not. Let's look at friction because we know that everything that friction's going to have, we're doing in the exact same way. So then, what's it actually doing? First, we need to find the work. We know we are going to travel some distance, but I don't have that distance. Yikes. Here's an idea. Let me cheat this a little bit. Let me start by finding the power. Let me find power first, and then let's talk about what that means. If I were to find the power, I need to take, essentially, remember that our equation right here is going to be something like power is equal to the force dotted with the velocity. Friction goes against our direction of motion, but at the end of the day, we're taking absolute values anyways. So I'm not going to worry about the negative signs here. I'm going to kind of breeze over that one. But they're pointing along the same axis, so there's no cosine or anything else like that to take into account here. Then I could say, all right, well, my friction force, based off of everything that I've got right here, friction force is going to be what? It's always going to be mu sub k, or just mu, times the normal force. The normal force, I see, balances out with gravity here. If the normal force balances out with gravity, then my friction force is mu mg. That's my total friction force. Come back to my power equation. I say power should be mu mg times that velocity. 1 times 0.6 times 10 times 9.8. What we find at the end of the day is a power of 58.8 watts. How do we feel about this so far? That's the energy, or rather, that's the power that we're putting in. That's the same power that friction is taking back out. We're moving at a steady speed. There is no change of the energy of the block. So everything acting on it is balanced in one way or another. Whether we're talking about forces, or work, or power, it's balanced. So now, let me take this. Let me say, hey, I know that power is the rate of energy, right? We have defined so far that power is that derivative of energy of the system. That is to say, if it's a constant rate, this becomes change of energy over change of time, or rather, the work done divided by delta t. So if I already have the rate of power, I can find the work done by simply multiplying it by the time that we're doing this. Work done by us, the work applied, is equal to the power applied times time. That's all we need, and I didn't calculate out this number. Where is this one? 58.8 times 3, we should end up with 176.4 joules. That's how much energy we put into this thing, and that is the exact same amount of energy that friction pulled right back out. Well, I'm going to say that's all I've got for today. Thank you guys so much for being here. I, of course, always appreciate it, but we're out of problems for now. That's the last of the material that's going to be on exam 2. Next time, we're back here for just working on review problems and diving into all of that stuff.